Are you ready?
What's that?
All right, let's go.
Hi, my name is Schwartz. I'm with Mainstream Engineering. We're in Rockledge, Florida. That's over by the Kennedy Space Center. And I'm going to talk about some of the ongoing work that we have regarding our CO2 separation from high humidity, low concentration environments using membrane electrode assemblies. And our interest in MEA technology really arisen from the unique opportunity. There's an issue with self-contained breathing apparatus systems or rebreathers in these closed-loop breathing systems. These currently employ packed absorbent beds to capture the CO2, and these generate an excessive amount of heat and moisture, which is a problem for the user, both in terms of operation and physiological problems. So what we're at now is we're moving on to scaling up this system to a full-scale prototype through a series of moving from single cell testing to a subscale laboratory prototype to demonstrate that we can move to a full-scale stack. So the basic system works by, as you exhale of your positive pressure full face mask, the CO2 enters a CO2 scrubber, and then your oxygen depleted stream enters a counter lung where a positive high pressure oxygen cylinder adds oxygen to the breathing loop based on what was consumed by respiration, and that's cooled through an ice pack to lower the humidity and the temperature down to the user so they can continue rebreathing in a closed loop. There's been a lot of barriers to new technology in this realm because of the governing agencies like NIOSH and OSHA, and it's really hard to push changes through. So a number of other challenges that we face with SCBA system development in terms of lowering the total size and weight, is you've got to remember the user who is doing this SCBA system you're typically under a very stressful environment. They're carrying equipment or tools, and their respiratory rate is going to fluctuate over time. So again, reducing the CO2 and reducing the size and weight of the system. So we've gone through and we evaluated a number of electric catalyst materials and electrode support materials and membrane materials that we use to develop these MEAs. We've gone through to fabricate singles MEAs, tested those under a range of conditions, and now moving to this laboratory prototype where we can scale the full system up, and then later on, when it comes to a manufacturing standpoint, increase the total electrode area. And there's a little bit showing again how we've gone through the screen number of catalysts and looking at their activity in order to try and optimize before moving on to the prototype development. So we used a surrogate breathing mixture, which is about 5% CO2, 50% oxygen, and 80% nitrogen, nearly fully humidified. And we tested under a range of flow conditions and measured the effluent CO2 concentration as a function of time, as well as over a number of current densities. And you can see here, we're actually able to get the CO2 concentration well below 1%, which is the target set forth by those governing agencies, and that the total current is proportional to the amount of CO2 being separated over time. So we're actually able to, currently as the state that we're at right now, achieve nearly 1% CO2 in the effluent stream for breathing rates up to 70% moisture. So we're going to achieve a very rapid transition to the prototype phase by using a low pressure drop single pass flow channel, and that's readily scalable. So you see this is a CAD rendering actually of the subscale laboratory prototype, which uses a 1/8 scale electrode surface area, and we're able to move quickly between subscale laboratory into a full-scale prototype by increasing the electrode area, which is more of a manufacturing issue than it is really the chemistry. So with this, we've been able to demonstrate that it is possible to achieve less than 1% CO2 concentration in the effluent with a multi-cell stack, and we demonstrate that there's no significant heat generation. So we're able to address the CO2 issue as well as the temperature and humidity control using MEA technology for these closed-loop breathing systems. We also demonstrate that this type of technology and this type of configuration is readily scalable, which is important for transitioning this to the market. And the other advantage that we found is that we were able to continue with MEA optimization and immediately implement that into the prototype as we move along and kind of hit in parallel optimization and prototype development.